Hello! In this practical example, we are going to consider the future development of a simulation to recover nitrogen from a ternary mixture of nitrogen, ethane and N-butane by liquid-liquid separation. For this purpose, we have downloaded the scientific paper which reports experimental values of the three-phase liquid-liquid vapor equilibrium of the system. This is a ternary system with a type 2 behavior. This means that there is one zone with two coexisting liquid phases and two zones, L1 and L2, with homogeneous liquid phases. A point which is prepared on the gray zone is split into two different liquids, L1 and L2, according to the corresponding tie lines. In order to illustrate the performance of the property package that we are going to select next, we have chosen one of the experimental tables reported in this paper. For example, the one corresponding to the N-butane rich liquid phase, which corresponds to the equilibrium line on the left side. From this table, we have chosen one single point, this one, to illustrate the performance for calculation of the property package. We are going to calculate this point using Aspen properties, and we will place the corresponding point on the ternary diagram comparing with the experimental results here reported. As always, the first step corresponds to the selection of the appropriate property package. According to the selection procedure described in Aspen, the first question is about the polarity of the system. All our three compounds are nonpolar. The second question is about the type of compounds, if they are pseudo-components or real components. All our components are molecular real compounds, so we have this proposal of property packages. From these 5 ones, we have selected the first one, Penn-Robinson. To develop the diagram, we start a new Aspen properties file. The first step is to define the components. Next, to select the property package, we have chosen Penn-Robinson. Now we have a required input incomplete, which corresponds to the methods folder. If you click on Next, the status turns blue, and the reason is that Aspen only wants you to check that parameters are available for the Penn-Robinson equation of state. They are available for the 3 binary pairs. To generate the ternary analysis, we click on the analysis group of the Home ribbon and select ternary diagram. Click on Continue. The components, the property method, and the type of equilibrium are already selected, and we only need to change pressure. If you look at the system, the pressure of our point is 35.61. Click on the button Run Analysis, and this is the calculated ternary diagram. As you can see, the second liquid region, L2, is so small that we cannot appreciate in the diagram. Now we need to represent our point. For this purpose, we are going to add an X to the diagram, and we will place it in the corresponding point to the composition 155,333. This is approximately the composition of this point, and as you can see, it is almost placed on the equilibrium diagram line, so the calculation is quite correct. The next question in our example is to identify the option codes in the selected equation of state. To find these values, we go to the Methods Selected Methods folder and open the method Penn-Robinson. Here we have a detailed description of all the methods, routes, and models for the Penn-Robinson property package. As we are interested in option codes, we click on the second tab, Models. Most of the properties refer to the same model, which is the Penn-Robinson equation of state with original literature alpha functions. If you click on any of the properties calculated by this model, and next you click on the option codes, you find the value for the 6 option codes used for Penn-Robinson. The meaning of these option codes can be found on the help system using this model name. Just typing the name of the model, the first option corresponds to the meaning of the option codes for different equations of state. Go down here until you find the one corresponding to Penn-Robinson. In the first option code, the option, remember, was 1. This means that the original literature alpha function is used in this property package. Other options are using the Boston-Matthias alpha function if the value of the option code is set to 0, the extended Gibson-Lafton for a value of 2, and so on for the rest of the options. The second option code, which value was 0, means that the standard Penn-Robinson mixing rules are used. If an alternative value of 1 was used, then the asymmetric mixing rule from Dow would be used. The third option code, also with a 0 value, means that it doesn't use steam tables, but the values of steam are also calculated by the Penn-Robinson equation of state. The fourth option code, with a 0 value again, means that the Penelux liquid volume correction is not used. To use this correction, you must change the value to 1 or to 2 if you want to change in both phases. In the fifth option code, the 0 value means that an analytical method is used for finding the root of the cubic equation of state. Alternative values, 1 and 2, can be used for a numerical solution. As you can see, the sixth option code is not described in the help system. Finally, in the last question of our example, we need to identify how the molar volume of the liquid mixtures is calculated and report the models and parameters which are used. The molar volume of the liquid mixtures is a major property, so we need to click on the roots page, look for the corresponding parameter, which is volume of liquid mixtures, and click on the view button to identify the corresponding root used in this property method. As you can see, the root is the simplest one. This means that the property is directly calculated by a model. The model used in this case is the API model for the liquid mixture. The name of the model is VLLE API. We go to the help system and ask for help on this model. The API liquid molar volume uses two different contributions, as shown here. The first one corresponds to pseudo components, for petroleum components, and the second one for real ones, as in our case. For pseudo components, you have here the description of the model used, and going down you find that for real components the mixture racket model is used. So we are going now to ask for help on the racket model. The Racket-Campbell-Todos equation is the one which is here described, where parameters are calculated according to these equations. Going down in the help, you can find the parameters table. As you can see, this model uses 5 different parameters. The first 4 ones are for pure compounds: the critical temperature, the critical pressure, the critical volume, a specific parameter for the racket equation, and the compressibility factor, also specific for the racket equation. Finally, a binary interaction parameter, KIG, is used. This parameter, KIG, is used as a mixing rule to calculate the critical temperature of the mixture. We can now try to find the value used for this parameter in our system. We go to Parameters, Binary Interaction, and click on the folder for this racket binary interaction. As you can see, this value is empty. This means that predicted values will be used. We can improve the calculation of the molecular volume of mixtures if you use a value for this parameter, which should be obtained from experimental molecular volume values. We can now calculate the molecular volume using the Penn-Robinson property package and compare it with this experimental value. For this, we need first to create a property set which includes the molecular volume. Click on New. We need here to define the properties you want to include in this property set. We are including the parameter volume for a mixture and the units the same that in the paper, milliliters per mole. In the second page, qualifiers, we specify the liquid phase. Now we go again to the analysis group in the home ribbon and select the mixture properties. We define the composition of our mixture. We select the property set. We specify as manipulated variable the vapor fraction, starting point 0 and final point 0. We only want the liquid phase, 1 point. And for the pressure, a single value, the experimental 35.61. We click on Run Analysis. The page of plots is open, but if you go back to the input form, and you click on the Results tab, you get the calculated value, 63. This value is 10% higher than the experimental value, and this calculation can be improved, as we said before, correlating the binary interaction parameter of the Racket equation.